We showed that superfluidity appears in a system of cold bosons due to global gauge invariant spontaneous symmetry breaking. The Lagrangian itself is invariant under global gauge transformation, but the ground state is found for a non-zero value of the vacuum, and that's because of the chemical potential, which enforces a given number of particles, at least in average. And this chemical potential is responsible for the spontaneous symmetry breaking. As a result, if we start from a ground state somewhere in the bottom of this potential and we apply a gauge transformation, we find another ground state. So that's a signature of spontaneous symmetry breaking. The Lagrangian is invariant, but the ground state is not. So this means that there is a Noether's current and charges which are conserved at the level of the Lagrangian, but not if we transform the ground state. So let's work out what is a conserved Noether's charge associated with global gauge transformation. We consider an infinitesimal transformation. Because there are two fields, phi and phi dagger, there are two terms appearing in the expression for the conserved current. And the conserved charge is the space integral of the time-like component of the conserved current. The second term does not contribute because we have no time derivative of phi dagger in the Lagrangian. Phi kills the particle in x, phi dagger creates one, and therefore phi dagger phi counts the number of particles in x. Integrated over x, that gives us the number of particles. So global gauge invariant spontaneous symmetry breaking means that the number of particles is conserved by the Lagrangian, because it's a good symmetry of the Lagrangian, but the ground state does not have necessarily a well-defined number of particles. What it means that when we canonical quantize, we have a particle number operator, and the ground state is not necessarily an eigenstate of this particle number operator. This means that the chemical potential is good enough to fix the number of particles in average, but it's not able to impose the ground state to have a well-defined number of particles. And that can be related to the fact that we usually fix the gauge angle in the ground state. So in the ground state, the amplitude of the field is square root of the density, which is fixed by the chemical potential, but the angle is arbitrary. And indeed, we can show that if we fix this angle, we therefore don't know how many particles we have in the system. So to show that, we rewrite the Lagrangian in polar coordinate in the complex plane, where ρ is the density of particle in x. So we have two fields, ρ and θ, and what I would like to do now is to determine the canonical momentum associated with θ. So for that, we need to isolate the part of the Lagrangian which depends explicitly on θ dot, the time derivative of θ. And we see that it is coming only from the first term. So that's the only term which involves θ dot, and from that we can calculate the canonical momentum pi for θ. So we see that the canonical momentum to the phase is the density. So if we want to canonical quantize, we need to impose the commutator between θ and pi to be equal to I times the delta function. So now we integrate over y. So the integral of ρ of y gives a number of particles. This is a fundamental relation in condensed matter which states that the phase and the number of particles are canonical conjugates. And in particular, this means that if we want to know the phase precisely, then we have no idea what the number of particles is, because these two things do not commute. That's a kind of Heisenberg uncertainty principle, but between the phase and the number of particles. And thus, by fixing my vacuum or my ground state to be somewhere in the bottom of the potential, I fix the angle θ, and therefore I don't know what the number of particles can be. But usually we are dealing with systems which have a finite number of particles. Let's take for instance an atomic nucleus. It has a given number of nucleons, an atom has a given number of electrons, etc. So we often want to restore this number of particles, and we see that what we have to do is to abandon the idea of fixing the angle theta and instead fixing the number n, and to do that we need to sum over all possible theta. So if we have no idea what is theta, we will have a good idea of what is n. So if we impose the phase of our ground state, we get a superposition of states with different numbers of particles. So our ground state for given theta is a coherent superposition of states which are eigenstate of the particle number operator. Now if we want our ground state to have a good number of particles, to have a well-defined number of particles, it needs to be also an eigenstate of n, and therefore we need to sum over theta. Indeed, we can show that by summing all the ground state for a given gauge angle theta with this exponential weighting, we find a ground state which has a good number of particles. So if we apply the particle number operator on it, we will find exactly n particles. This technique, called particle number projection technique, is particularly useful when the number of particles is small, like in an atom or in a nucleus, for instance, because in that case it's often not satisfactory to just know the number of particles in average.